back. My name is Tyler Lemmond. I'm trying desperately to learn all that I possibly can with tech, all the things that go along with that stuff. And I'm trying to get my CCNA. If that is you, then you've come to the right place. If that's not you and you want to come and chill, then that's what's going on. If you were here for last night's stream of Halo and all the shenanigans that went on with that, thank you very much. And if you came to see both, thank you even more. Make sure to like, subscribe, and share. Put a comment, jump in the chat, whatever it is. What we're going to be doing today is we're going to be doing day 10 IPv4 headers. So a lot of people like to think, really, when I do these streams, all anyone wants me to do is subnetting, which we will do some of that. That will be a thing that will happen. And I do have, let's see here, my little worksheet here that we will go through. That'll be at the end, but we definitely need to do some Anki cards, and we need to do a little bit of back pay from some of the Anki cards, some of the flash cards, because we didn't do them last time, and I don't think we did them the time before that. But we definitely need to knock through those things. Oh, we need some jams, don't we? There we go. There we go. Sick. Yep. Okay, just making sure that it that it's playing the music and it sounds good and whatnot. Okay, so we are gonna do this. That is a thing that will happen. And we're gonna go ahead and we're gonna jump onto this. I always say that we're probably there's always a slight chance that we won't watch the whole video, or that I'll skip around or something like that, because it is true. I am just trying to learn it just as much as everybody else. So that means that I might back up, I might move forward, I might skip a spot or anything like that. If you're not subscribed to Jeremy's Tech Lab, you definitely should be. He's really, really, really good. Yeah, he's really, really good. You should watch his videos. They're absolutely phenomenal. But let's go ahead and let's jump into it.
T-Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment and share the video to help spread this free series of videos. Thanks for your help. Also, remember to download and use the Anki flashcards with the link in the description, which will help you very much in remembering what you have learned. Let's get started. In this video, we're going to take a look at the Internet Protocol version 4, known as IPv4 header. This is used at layer 3 to help send data between devices on separate networks, even on other sides of the world over the internet. This is known as routing. Originally, I planned this video to be a general introduction to routing, but in the end, I decided to split it up into separate parts. Let's take a look at what we'll cover in this video. We'll cover the IPv4 packet structure, or more accurately, the IPv4 header, which is used to encapsulate a TCP or UDP segment. Specifically, we will cover the fields of the IPv4 header. We already looked in detail at two fields of the header, the source and destination IP address fields, but there are quite a few more fields to look at. And that's all for this video. As I said, I originally planned to make this a long introduction to routing video. However, I don't want to make these videos too long. Already the shortest videos are at least 30 minutes, which is quite long, I think.
Yeah.
So I decided to split up routing into more videos. This prevents the videos from getting too long, but also lets me go more in depth on each topic. So this video will focus exclusively on the fields in the IPv4 header, and then future videos will get more practical, with hands-on configuration in the CLI.
Okay.
Since we're going to look at the IPv4 header...
That explains why there's not a packet tracer for this one.
Let's review its position in a complete frame. So, the upper layers of the OSI model prepare some data to be sent to another device. It is encapsulated in a layer 4 header, typically using the TCP or UDP protocols, which we'll talk about in a future lesson. This combination of data plus layer 4 header is called a segment. The segment is encapsulated with a layer 3 header, usually using the Internet Protocol, IP. This combination of data, layer 4 header, and layer 3 header is called a packet. Then the layer 2 header and trailer are added, and this is called a frame. These units are called protocol data units, or PDUs. For example, the layer 3 PDU is a...
Now, I don't think it matters if it's on this side or if it's on this side. I think it just matters that whatever direction the data is flowing, like if I'm the computer over here and I'm sending to a computer over here, then obviously the header is going to lead, and then vice versa. I don't necessarily think that that necessarily is real or matters in the real world, because like the header just is what is coming out of the computer, or I could be totally reading way more into it and it's not that deep.
Is a packet, and the layer 2 PDU is a frame. For this lesson, we'll focus on this layer 3 header, as it contains the information that is needed to route this packet.
What happened? What?
To its destination.
There it goes.
Note that since we'll be focusing on layer 3 here, I'll usually be using the term packet, talking about routing packets rather than frames. So, thanks to Wikipedia for this chart of the IPv4 header structure.
Whoa, okay, so this is cool. Because we know that it's a 32 bits long, and the reason we call it 32 bits long is because we count 0. Don't ever forget that we count 0, because that can be a huge problem. Just in general, not just with this, but like all things. Wow. And it just keeps getting stacked. Okay.
As you can see, it's a bit more complicated than the Ethernet header. To be honest, I doubt that it'll be necessary for you to memorize the exact structure of the header, the size of each field, etc. for the CCNA test, but I can't make any guarantees. I didn't make the test. What I recommend is just getting to know the purpose of each field of the header, which we'll cover now. By the way, if you're wondering how to read this chart, it's left to right, top to bottom. So, this is the first bit of the header, and this is the last bit of the header. So let's quickly go through each field of the header so you're familiar with its purpose. First up is the version field of the header. Its length is 4 bits, half of 1 octet. Its purpose is straightforward.
A nibble.
It identifies the version of IP used. Now, there are only 2 versions of IP in use. IPv4, which is simply identified with the value of 4 in this field, or 0100 in binary. The other version is IPv6, which is identified with a value of 6, or 0110 in binary. Now, you may wonder what happened to IPv5. Well, there was an experimental protocol called Internet Stream Protocol, which uses an Internet Protocol value of 5, but it was never publicly used. So you could say that's the lost IPv5.
I think the government
Now, we're focusing on the IPv4 header, so this field of the header will always have a value of 4. The IPv6 header has a different structure than the IPv4 header.
I think that's how they're able
so if
to
the value
hide
of this field
things.
is 6, the rest of the header will also have a different structure. Next up is the Internet Header Length, or IHL field. It's also 4 bits in length, half of 1 octet. The final field of the IPv4 header, options, is variable in length, so this field is necessary to indicate the total length of the header. Here's an important part to remember. This field specifies the length of the header in 4-byte increments. For example, if the value in this field is 5, 5 times 4 bytes is 20, so that means that the length of the header is 20 bytes.
Okay.
The minimum value in this field is 5, which as I just said is equal to 20 bytes. That's the length of the IP packet without any IP options at the end, so an empty options field. The maximum value is 15, which is the maximum value of 4 bits. As you can see here, the value of the 4 bits are 1, 2, 4, and 8.
Okay,
Adding them up results in 15. So 15 times 4 bytes is equal to 60 bytes. That means the maximum length of the IP options field is 40 bytes. So an IPv4 header with no options field is 20 bytes in length, and that's the minimum length of an IPv4 header.
Okay.
And an IPv4 header with a maximum length options field, 40 bytes, has a length of 60 bytes, and that's the maximum length of an IPv4 header. Okay, that's the IHL field of the IPv4 header. Next is the DSCP field. DSCP stands for Differentiated Services Code Point, and the field's length is 6 bits. This field is used for QoS, Quality of Service. Basic
Yes.
QoS is a topic on the CCNA, so I will make a dedicated video about it later.
Ow.
Essentially, it is used to prioritize delay-sensitive data,
Ooh,
such as
man.
streaming voice and video.
Someone just stabbed
If
my
you're loading a
foot.
web page and the internet is a little slow, it's not a big
For
deal.
some reason.
However, if you're having a Skype call and there's terrible delay, or the audio and video keep freezing,
Skype
it can
call.
totally ruin the experience. This field is used to identify which traffic should receive priority treatment. Next up is the ECN field, which stands for Explicit Congestion Notification and has a length of 2 bits. It provides end-to-end notification of network congestion without dropping packets. Normally in a network, if the network is super busy, if there is congestion, this is signaled by dropping packets. The ECN field provides a way to signal a congested network without dropping packets. However, this is an optional field that requires both endpoints, as well as the underlying network infrastructure, to support it. Next up is the total length field, and its length is 16 bits, or 2 octets, 2 bytes. It indicates the total length of the packet, including the IPv4 header and the encapsulated layer 4 segment, which includes both the layer 4 header and the data. This is different than the IHL field, which indicates only the length of the IPv4 header itself. This field indicates the length in bytes, not in 4-byte increments like the IHL field. So, a value of 20 in this field simply means 20 bytes.
Wow, okay.
The minimum value in this field is 20, meaning 20 bytes, which is equal to a minimum-sized IPv4 header with no encapsulated data. the maximum value is 65,535, which is the maximum value of 16 binary bits, all set to 1. Let me just show you that calculation.
Hold on. Oh, 16 bits because it's 2 bytes, but we don't call it bytes, we call it bits because of reasons.
Here are 16 bits, 2 octets, all set to 1. The first bit is equal to 1, then 2, then 4, 8, 16, 32, 64, 128. This is as far as we went when looking at a single octet in an IPv4 address. If you extend beyond 8 bits, the value keeps doubling. Next is 256, 512, 1024, 2048, 4096, 8192, 16384, and then the 16th bit is 32,768.
Dang.
Add those all up, and you get 65,535, the maximum length of an IPv4 packet.
Jesus Christ. Oh my gosh. I mean, I'm good at doubling stuff, but I kind of tap out right around the 2048. Like, oh my gosh.
Next up is the identification field, which is also 16 bits in length.
This is a lot of information.
If a packet is fragmented due to being too large, this field is used to identify which packet the fragment belongs to, so it can be reassembled again to make the original packet. All fragments of the same packet will have their own IPv4 header with the same value in this field, so they can be reassembled later. Packets are fragmented if larger than the MTU, which stands for Maximum Transmission Unit. The MTU is usually 1,500 bytes. Remember the maximum size of an Ethernet frame? I mentioned that the maximum payload size of an Ethernet frame is 1,500 bytes, so these are related. And one last point, fragments are reassembled by the receiving host. Next is the flags field, which is 3 bits in length. It is used to control and identify fragments. There are 3 bits, and they function like this. The first bit, bit 0, is reserved and always set to 0. Bit 1 is the don't fragment, or DF bit. If it is set to 1, it means that the packet should not be fragmented. Bit 2 is the more fragments, or MF bit. It is set to 1 if there are more fragments in the packet, and then set to 0 for the last fragment. Also, if the packet is a whole, unfragmented packet, the MF bit is set to 0, since there are no fragments.
Interesting.
Next, we have one more field related to packet fragmentation. That is the fragment offset field, which is 13 bits in length. This field is used to indicate the position of the fragment within the original unfragmented IP packet. This allows fragmented packets to be reassembled, even if the fragments arrive out of order, since this field lets the receiver know the original order of the fragments. Next up is the time to live field, which is 8 bits in length. A router will drop a packet with a TTL of 0. So, this field is used to prevent infinite loops.
TTL, time to
live. If a poor routing configuration causes a packet to be continually sent around in a loop, never reaching its intended destination, if enough traffic like that accumulates, it could cause network congestion and eventually failure. This feature prevents that from happening, causing looped traffic to be dropped when the TTL reaches 0. This feature was originally designed to indicate the packet's maximum life.
That's also, if I remember correctly, that's also how you can attack people, because you can make it where their time to leave or their time to live is like infinite. So packets are just always bouncing around on the network, and then it dogs down the network for whatever it is. I think it's the difference between a DOS attack and a DDoS attack, but don't quote me on that. It's been a long time since I've looked at cybersecurity, attacking things, whatever. Anyway.
Time in seconds. In practice, however, this actually indicates a hop count. Each time the packet arrives at a router on the way to its destination, the router decreases the TTL by 1 until the packet reaches its destination, or the TTL reaches 0 and the packet is dropped. The current recommended default TTL is 64. Next up is the protocol field, which is also 8 bits in length. It indicates the protocol of the encapsulated layer 4 PDU. Typically,
okay, what I have a hard time with is visualizing this. I know that this is all virtual, but it makes it easier for me to visualize something going through a wire. So I don't know. I guess I think of it in terms of it's a tunnel, and then the packet itself, or the segment, all the data is a train. But what I have a hard time understanding is that it gets really long, but it also gets really thick too. So I don't know. I have a hard time wrapping my head around that.
This will be one of the following: TCP, which is indicated by a value of 6, or UDP, which is indicated by a value of 17. I haven't talked about TCP and UDP yet, but I will make a dedicated video about them later. For now, try to remember the protocol numbers of 6 for TCP and 17 for UDP.
One
You might also see a value
checks,
of
one
1,
just throws.
which is used for ICMP, the protocol ping uses. Another one to remember is 89, which is OSPF, which stands for Open Shortest Path First. OSPF is a dynamic routing protocol, which allows routers to learn routes to destinations from their neighbors, without us having to manually configure the routes. We will cover OSPF in depth in this course, so for now just try to remember the protocol number of 89. If you're curious, you can check a list of protocol numbers at this page on Wikipedia. Don't worry about memorizing any others, but try to remember these 4. The included flashcards are extremely useful for remembering little facts like these.
Yep.
Next is the header checksum field, which is 16 bits in length. It is a calculated checksum used to check for errors in the IPv4 header. When a router receives a packet, it calculates the checksum of the header and compares it to the one in this field of the header. If the newly calculated checksum and the checksum in the IPv4 header do not match, it means that an error has occurred in transmission, so the router drops the packet. Note that this is only used to check for errors in the IPv4 header, not in the encapsulated data. IP relies on the encapsulated protocol to do that. Both UDP and TCP, the 2 layer 4 protocols most likely to be encapsulated, have checksum fields to check for errors in the encapsulated data. Okay, next up are the source and destination IP address fields, which I covered in detail already. As you already know, they are 32 bits in length each, as that is the length of an IPv4 address. The source IP address field indicates the IPv4 address of the sender of the packet. The destination IP address field indicates the IPv4 address of the intended receiver of the packet. Finally, the options field, which is optional and can be 0 bits in length if not used, or up to 320 bits, 40 bytes in length. This field is rarely used. However, if the IHL, Internet Header Length field, is greater than 5, it means that options are present. Here is a chart from Wikipedia showing the structure of the options field. You can check it out or read more online if you're interested. But for the purposes of CCNA studies, I don't think you need to worry about it.
Okay. Well,
Okay, now we've covered all of the fields of the IPv4 header.
that was a shit ton of information. Okay.
It's a bit more complicated than the simple Ethernet header and trailer we already learned about.
Yes.
But hopefully you understand the purpose of each field now. For the purpose of the CCNA, I think the information presented in this video is sufficient. But of course, feel free to read.
I also don't understand the difference between an Ethernet header and an IPv4 header. Can we do a detour real quick? What is the difference between between a Ethernet header and a IPv4 header? Okay, let's let that cook.
Read more, a simple Google search will give you many good resources. Also, don't forget to use the Anki flashcards to help you remember everything.
Yeah.
Now let's go in depth and analyze a packet capture from Wireshark.
Okay.
I showed you Wireshark before, and it's an extremely useful tool both for learning and also in the real world to troubleshoot problems. This isn't a Wireshark course, but I will show you Wireshark at various points in this course.
Crazy.
And if you have a lab with real Cisco equipment, or a virtual lab using GNS3, I highly recommend you use Wireshark to examine network traffic like this. It will really help you in your studies. But in either case, I will show you Wireshark packet captures in this course, so don't worry if you aren't able to use it yourself. So, I sent a ping between 2 routers. Notice under the info column it says echo ping request. I have selected the frame here, meaning the entire frame, and you can see down here that the entire frame is highlighted. These digits are a hexadecimal representation of the frame. Now I highlighted the Ethernet header, and down at the bottom you can see only the Ethernet header section of the frame is highlighted.
Oh, shit. Okay. So that it's the same thing, just with no colons. Honestly, I think it's easier to read with spaces.
Highlighted. Then I highlight the IP header, and at the bottom, only the IP header section of the frame is highlighted. Then I highlight the packet's payload, which is Internet Control Message Protocol, or ICMP, the protocol used by ping, and you can see the payload highlighted at the bottom. In this video, we're focusing on the IPv4 header, so let's expand the Internet Protocol version 4 information. Okay, so I've expanded the IPv4 header section.
Okay, hold on. Let's see what it says.
Quick note first. I'm assuming you mean the Ethernet header. Withernet isn't a standard networking term.
Whoops.
If you meant something else, let me know. The 2 headers live at different layers of the stack and solve different problems. Ethernet header, layer 2, data link. It's just 14 bytes, destination MAC address, source MAC address, and an ether
Okay,
type
and
field.
this is what he said in the beginning of the thing. The Ethernet header lives at layer 2, and the IPv4 header lives at layer 3. So these are all just headers that keep getting put in the long line of string of data that is going through the wire. And then, of course, it has its own layers that are in that as well. That's so crazy, because in my mind I originally thought it was one dimensional, like it was just like little chunks, but in those chunks there's like crap in it, as we can clearly see.
And zoomed up a bit. And here you can see all of the fields we looked at in this video, except options.
Yeah, the header
As I said,
bytes
options
20.
are rarely used, and they aren't in this packet.
We talked about
First
that.
up, the version field. And you can see the binary bits 0100 on the left, and it shows you that means version 4. Next is the header length, which is the IHL field. It has a binary value of 0101, which equals 5.
But where's the thing
Remember,
with the
this field
H?
indicates the length in units of 4 bytes. So this value of 5 means a header length of 20 bytes. That is the minimum header length, and it is the length of an IPv4 header with no options field.
Okay.
Next
no
up is the
option field.
differentiated services field. And as you can see, Wireshark categorizes both the DSCP, differentiated services code point, and ECN, explicit congestion notification fields, under this section. Both are set to 0 as they are not being used. Next up is the total length. This represents the total length of the IP packet in bytes, including both the header and the ICMP data it encapsulates. So,
okay, hold on. I want to compare this.
20 bytes.
Yeah, can we make it big? I want to make it big. Jesus Christ, dude. Where is it? There it is. Okay. So, any other time I accidentally do it. Okay. So, we have this. We have version. Any other time it, like, makes it do the thing. Whatever. Okay. So, we have the version. This was not a part of it. Then we have DSP. Hold on. Let's make this even better. So we have version, the header length, okay, which is 20. So we don't have this. Because the 20 is the minimum length. That makes sense. Then we have DSCP right here. Then there's our ECN 0. Our total length is 100. That's our total length. Which is crazy because we have up to like 65,000 bits or something like that.
So this 100 means that the total length is 100 bytes. Next is the identification field. This packet has an identification field of 5. It's not fragmented, but if it were fragmented, the other fragments belonging to this packet would also have a value of 5 here.
Okay.
Next up is the flags field. Notice that Wireshark also includes the fragment offset field under this section. The reserved bit is always 0. That's what not set means, by the way. I sometimes say set to 0 or set to 1, but another way of saying it is not set, which means 0, or set, which means 1. The don't fragment bit isn't set, so this packet...
The first comment is, this is the first video where I'm like, whoa, that was a lot. Yes. Yes, I agree.
Can be fragmented if necessary. The more fragments bit also isn't set, which is expected as the packet isn't fragmented. The fragment offset field
Okay.
is 0, which is also expected in a packet that isn't fragmented.
I'm going to have to look at a lot of, like, packets in Wireshark.
Remember, the time to live field is 8 bits in length, and 255 is the maximum 8-bit value. The protocol is ICMP because I used ping. Notice the protocol value of 1, which indicates this. You can see the header checksum here. Remember, it's a 16-bit value. 0x indicates hexadecimal, and then each hexadecimal digit is equal to 4 bits. So 4 times 4 is 16, 16 bits.
Okay.
Here's the source IP address, and finally, the destination IP address. The standard ping command on a Cisco router will send 100-byte pings, which is why the ping I showed you wasn't fragmented. But I pinged once more using this command. Ping 192.168.1.2, size 10,000.
Whoa.
Sent 10,000 byte pings, much larger than the 1,500 bytes MTU. So this will cause fragmentation. As you can see here, there are a bunch of IP fragments. They all say reassembled in number 13. What is number 13? Well, it's this ICMP echo request right here. Now let's take a look at some of the IPv4 header fields in these fragments. Okay, so these are the details of just the first 2 fragments. First,
Okay. I'm going to keep that open just in case. But
First off, notice the total length of 1,500 bytes. So this 10,000 byte ping was divided up into 1,500 byte fragments, which is equal to the MTU size. Then notice the identification field of 1. This is different than the last packet I showed you, but notice that the value is the same for these two fragments. Then take a look at the flags. Each of them has the more fragments bit set, because neither of these is the last fragment in the packet. Also notice that each of them has a different fragment offset value, and that the first fragment has an offset of 0. Just one more thing. This time I sent a ping and set the don't fragment bit by adding the df bit option to the ping command. As you can see here, now the don't fragment bit is set. Because I didn't set the size, the default ping size of 100 bytes was used, so it was no problem that these packets weren't allowed to be fragmented.
so what is the benefit of fragmenting something and not fragmenting something? What is the benefit of fragmenting or not fragmenting a... Whoops, that is not how you spell benefit. What is it that we're fragmenting? The like... IPv4 header. Okay, let's let that cook.
However, if I send pings that are larger than the MTU and set the df bit, you can see the pings fail. They were too large to be sent unfragmented, but also not allowed to be fragmented. Before moving on to today's quiz, let's review what we studied. We looked at the structure of an IPv4 packet, more specifically, the fields of the IPv4 header. That's it.
Yeah.
It doesn't look like a lot when you list it like this, but I'm sure you agree that was a lot of information.
Yeah,
In the next video,
Holy
we'll get
shit.
more practical and hands-on, getting into the CLI to see how to configure routes.
I understand. Why
Okay,
there's
let's
not
move on to
package
today's
tracer.
quiz. In addition to the quiz, make sure to download and use the Anki flashcards to help you remember all of the details you learned in this video. Let's get started with question 1. What is the fixed binary value of the first field of an IPv4 header? A, 0010. B, 0110. C, 0001. D, 0100. Pause.
I'm sure that he said this, but I feel that we didn't go over that. Okay, let's see what it has to say.
Fragmentation exists to solve one problem. The packet you're sending might be bigger than the MTU, maximum transmission unit, of some link along the path. Ethernet's MTU is typically 1,500 bytes, but a tunnel or older link in the middle might only carry 1,400. The IPv4 header's identification, flags, and fragment offset fields let a router chop the packet into pieces that the destination host reassembles. The DF, don't fragment, flag lets the sender forbid this. The benefit of allowing fragmentation is robustness without prior knowledge. The sender doesn't need to know anything about the path. It can fire off a large packet, and any router that hits a smaller MTU link will split it up. Delivery succeeds across heterogeneous networks transparently. This mattered a lot in the early internet, when link types varied wildly. The benefit of not fragmenting, setting DF, is efficiency and reliability, and it's why DF is the modern default. Fragmentation has real costs. If even one fragment is lost, the destination can't reassemble, and the transport layer must retransmit the entire original packet, so loss gets amplified. Reassembly burns memory and CPU at the receiver. Only the first fragment carries the TCP UDP header, which confuses firewalls and NAT, and enables classic evasion attacks, tiny fragment, overlapping fragment. And fragmenting, mid-path, is expensive work for routers. Setting DF also enables something better, path MTU discovery. When a DF packet hits a link it can't fit through, the router drops it and sends back an ICMP, fragmentation needed message containing the smaller MTU. The sender then shrinks its packets to fit the path end-to-end, right-sized packets, no fragmentation anywhere. TCP relies on this. The one gotcha: if a firewall blocks those ICMP messages, PMTU'd fails silently, and large packets just vanish. The black hole problem, which is worked around with MSS clamping or probing-based discovery. The verdict from history is telling. IPv6 removed in-network fragmentation entirely.
Wow.
Routers drop oversized packets and tell the sender. Only the source may fragment. Avoiding fragmentation 1.
So, okay, if IPv6 is so much better, then like why do we still use IPv4 for like all private stuff? Is it just because doing private IPv addresses is just easier? Because it's like it's easier to mess with on a small private scale? But then I would argue that like a giant like corporation building or something that's like in New York or Houston or LA or Miami, you know, like one of these giant skyscrapers that just has like buildings of like floors, I would say I would ask, like, is it really easier to do all that? Like, I don't know. Anyway, let's get back to the quiz.
Pause the video to think about your answer.
I think it's D.
The answer is D, 0100. The first field of the IPv4 header is the version field. Because the question is about an IPv4, or Internet Protocol version 4 header, the version field is always set to 4, or 0100 in binary. Let's go to question 2. Which field will cause the packet to be dropped if it has a value of 0? A, TTL.
TTL,
B,
time to live.
DSCP.
Yes.
C,
Easy.
IHL.
Easy money.
D,
A.
ECN.
Final answer.
Pause the video to think about your answer.
Don't need to. TTL.
The answer is A, TTL. TTL stands for time to live. It is reduced by 1 at each router the packet passes through. If it reaches 0, the packet is dropped. Let's go to question 3. How are errors in an IPv4 packet's encapsulated data detected? A, the IPv4 header checksum field checks for errors. B, the encapsulated protocol, for example TCP or UDP, checks for errors. C, errors in the encapsulated data cannot be detected. Pause the video to think about.
Okay, so this is a trick. The encapsulated protocol TCP UDP checks for errors. TCP does, but UDP doesn't. It's checksum.
Your answer. The answer is B. The encapsulated protocol checks for errors. The IPv4 header checksum field only checks for errors in the IPv4 header itself. However, layer 4 protocols like TCP or UDP can use their checksum to check for errors in the encapsulated data. Let's go to question 4.
Wow, I got it wrong.
Which field of an IPv4 header is variable in length? A, options. B, header checksum. C, total length. D, IHL. Pause the video to think about your answer.
The field of an IPv4 header is varied in length.
The answer is A, options. The options field can vary in length from 0 bits to 320 bits. The other fields are fixed length. Although the total length and IHL fields are used to represent the variable length of the IPv4 header and packet, the fields themselves are fixed in length. Let's go to question 5. Which bit will be set to 1 on all IPv4 packet fragments except the last fragment? A, fragment offset bit. B, more fragments bit. C, don't fragment bit. D, packet fragment bit. Pause the video to think about your answer.
I think it's A, fragment offset bit.
The answer is B, more fragments bit.
Damn.
The more fragments bit, part of the flags field of the IPv4 header, is used to indicate that the current fragment is not the last fragment of a fragmented packet. It is set to 1 on all fragments except the last, which will set it to 0. A, fragment offset, is a 13-bit field in the header, not a single bit. C, don't fragment bit, is used to prevent a packet from being fragmented. And D, packet fragment bit, is not a real bit in the IPv4 header. Okay, that's all for the quiz. Remember to use the supplementary materials to help you remember what you've studied. There will be Anki flashcards to help you review what you've studied.
Yeah, we're going to do that.
For a video like this, I think the flashcards are particularly important, so remember to download and use them. There will be a packet tracer lab for routing, but not after this video. Wait until after day 11's video to get some hands-on practice configuring routing on a Cisco router. Good luck with your studies. Thank you for watching. Please subscribe to the channel, like the video.
Yeah, if you have not subscribed to Jeremy's Tech Lab, you definitely should. It is really, really good. Some really good stuff. All right. Dang it, dude. No one wants that Windows. Go away. I just want to be able to control my window. Oh my gosh. Oh my gosh. Okay. So here's what we're going to do. We're going to work on this right here. Okay. I, contrary to popular belief, have gotten better. Why is that not showing? Oh, because I need to move it down myself. Actually, no. That's fine. That's fine. We'll be here. Yeah. That's fine. Okay. We can even make it a little bit bigger. Okay. So, let's get started with this. We're gonna do one, maybe two of these. Okay. Practicing this stuff. We go here. Boom. Flip. Thank you very much. Do I already have a layer set? There we go. Okay, so we have 215, 231, 105, 193, and 29. Okay, I'm not going to waste the time to turn it into binary. If you really want me to make it into binary, I will. But I'd rather just keep moving forward because that doesn't really matter when it comes to subnetting. So what we're looking for is we're looking for the 29 right here. The 29 is this. 1, 2, 3, 4. And I don't actually need to count them because they're octets, right? So that's 8, 9, 10, 11. And I'm not going to always put X's on them. But, okay, so that's 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So the line is right here. Everything that's here is frozen. Okay? Everything that's here is free. Okay? So that means that we have these over there that are frozen. All right, so let's talk about the network bit size. That is 29, which means that our CIDR check is 29. Now we're going to build the mask. This is how we got 29. The way we got 29 is that we added up all of the octets. So this whole octet's being used, this whole octet's using, that whole octet's being used, and then 1, 2, 3, 4, 5. So we have 8 plus 8 plus 8 plus 5, which is 29. Okay, so that tells, so then we ask ourselves, okay, so then what's the mask? What's the subnet mask? So when all of these are being used, and again, that's why I didn't make it into binary, because it doesn't matter if it's a 1 or a 0, because it's still being used. Even if it's 0, it's still being used, because there was another one that followed it. Okay. Whoops. So that means that this is 259, or 255, 255, 255. My handwriting's fat. Plus these 5 right here. So we need to add these up. Boom. So we need to add those up. Let's do that real quick. My brain's a little broken from Halo last night, so we're going to do a calculator. 128 plus 64 plus 32 plus 16 plus 8. 248. 248. Now, our wild card is what's left over. That's the best way to think about it. So 1 plus 2 is 3 plus 4 is 7. We'll talk more about wild cards like later. All right. Now let's discuss what's the interesting octet, which means which one is split, and that would be the 4th octet. And this right here is probably the hardest part. Okay. This is probably the hardest part, in my opinion. It was the hardest part for me to understand. So the mask value in that octet is what we're going to do. We're going to add it together. Yes. Which is going to be 7. The block size is 256 subtract 7. So that's 16. That's 4. 7. That's 9. That's a bad 9. 9. 4. And then 2. So our block size is 249. Which means that our crap, dude, I forgot. Yep. Okay. So all this added together is this. Okay, so that's correct. Oh, that's what it is. It's multiples. It's multiples. So what we need to do is we find multiples of this and we keep going until we hit the target. And the target is this. So 8 goes into 248, the lowest common denominator, 208 times. Should. Let's double check that. 8 divided by 248. No, that's not it. Okay, maybe if I do 8 divided by 208. Sorry, I always say it backwards. $208 divided by 8 is 26. Where did we get 26 from? Dang it, dude. I spent all day yesterday like practicing this. Because this target octet, this right here is what what the network is based on. The hell was that? Hold on. Cats just knocked over a bunch of crap, that's all. Not a big deal. It has to do with multiples of this. Okay, it's how many 8s can go into 148. But there's no way that... No, it's not how many, it's how close. That's what it is. So 248 divided by 8 is... No, so then what's the target? Oh! The target is this. It is how many 8s can go into the interested octet. Yes. So that means, and then you drop the remainder. Yes, it is all coming back to me now. So 211 divided by 8 is 26 with the remainder of 3 8s. Okay. That's still not it. But no, that has to be it. So then 26 multiplied by 8. And then 26 multiplied by 8. Okay. This is some tomfoolery math. I'm not going to lie. So. Well, and I'm going to do this in a different color. How about purple? Gross. Okay. So we take our block size, which is... For us right now, it's 249. And we ask ourselves, how many times can it go into 105? This number right here. Okay. it can't go into it at all. So it's 0. So that means our target is 0. So that means our network here, and I'll be a good boy. I feel like that's not right. Okay, whatever. I don't care. I tried. Try to keep it the same. Our bits that are free is 7. And then we take 2 to the power of 7 to get our addresses. So 2, I have a calculator right here. 2 to the power of 7. So 128. So 128. Yesterday, someone asked me, like, why do we subnet? This is why. Because we just made a subnet that only has 128 addresses in there. And it's segmented to just that. Okay. Now, our usable is 127. Or, sorry, 26. Because we can't use the first one and we can't use the last one. Which means that our host, God, I hope this is right. 215, that's correct. 231, that's correct. 105, that's correct. And 0? Let's test it. Okay. 215.231. Why is it not writing? I hate when my numbers lock just decides to turn off. 231, 105, 0. Let's find out. Am I right? Why is it 92? How did it get 92? I must have screwed up here. All right, Claude. Tell me the errors of my ways. I am still struggling with figuring out the target octet. Where did I go wrong? All right, let's let it cook. I bet I went wrong with the mask value. But I'm pretty sure the mask value is all that stuff added up. Shoot. So let's see here. 255 plus 1 plus 2 plus 4. Oh, it's not that. $128 plus 64 plus 16 plus 8. So how in the world did we get a mask value in the octet of 248? 128 plus 64 plus 32 plus 16 plus 8. Oh, I added the wrong shit. Okay. This is not correct. It's actually this stuff added together. Okay, before we read Claude, let's see if we can figure it out on our own. So that'd be 128 plus 64 plus 32 plus 16 plus 8, which is 248. So then that means all this is wrong. That means what we got to do, I'm going to do it over here. 256 248. 16, 4, 8, 0, 0. So that means that our block size is not this. It's actually 8. So then, how many times can 8 go into this? So 193 divided by 8 is 24. We drop it. So 8 multiplied by 24 is 92. So that means our target is 192, which turns this into 192. Is that what you're going to tell me, Claude? Yes. The block size is 8. Okay. 2 sanity checks that will catch errors instantly next time. First check octet plus wildcard must equal 255. Oh, well, yeah, I guess that makes sense. Whoa. No. So then this is the subnet. Okay. All right, let's do it again. We'll do one more. Here we go. 10 to 18. Whoops. 27, 201, 26. All right. We can do this. Let's make hell, we'll do red again. I don't care. So all of this is being used. All of this is being used because that's 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So the cut is right here. Okay. So that is all of our frozen bits. Okay. And it should be 26. So that's our side R, 26. Okay, how we got that is 8, 8. That doesn't look like an 8. That still does not look like an 8. Come on, get it together. 8, 8, 2. So 8 times 3, 24 plus 2, 26. We are correct. Which means that it is 255, 255. That looks like a 3. 255, and it is 128 plus 64, which is 192. Which means that our wild card is 1 plus 2 plus 4 plus 8 plus 16 plus 32, which is 113. 113 plus 192. Something didn't go right. 128 plus 64. Okay. Whoa. We don't need it to be that big. Thank you. Good thing we double checked. Okay. So this is actually 82. We can double check because 113, 82. Add those together. 3 and 2 is 5. That is 9, and that's 195. That's still not correct. Still not correct. Plus 64. No, that what? Wait, what? What? That what? Okay, hold on. Because this is about to screw us all up if we don't do this correctly. Okay. So we need to add these together to create this. So that's 128 plus 64, which is 192. Then we add these up to get the wild card. 1 plus 2 plus 4 plus 8 plus 16. $31. I don't know what happened there. We're still missing 2-bit. We're still missing a lot of bits. Oh, because I didn't. God, dude. I loathe the touchscreen. Okay, now let's try it. 65. Now this should be right. It's crazy how like basic addition can totally fuck you up. 7, 8, 7, not 7, 5. This is already not right. This is already not right. It's supposed to equal 255. Yes, because it's not 65. Oh, God, dude. $32, not 30. I had a 34. 192, 63. 5. 9's 5. Okay. Check. Done. 0, 0, 0. Okay, let's switch to blue. Okay. So this is the interesting octet, which is 4. Okay. This tells us how many bits are free. Our mask value octet is... Now, this is where I screwed up last time. I don't think it's those added up. I think it's these added up. Let's double check. Yes. 128 plus 64. 4. That's 12. 132. Yes. So the mask value in that octet is this right here. So 128 plus 64 is 192. So that means that these two numbers are always the same. Is that true? No. Yes. Look, damn it. Right here. Right here. Okay. So then now we take 256. And the reason it's 256, not 255, is because we count 0. 192. Let's make that better. 6 is 4. 15. 1. 5. 9. That should be 14. That should be 4, right? Wait, what am I doing? 5, 6, 7, 8, 9. 6. So our block size is 64. Now, what we need to do is figure out this. And this is going to be this number And how many times it goes into that? So 64 divided by 201. So it's 3 point... Really? That's kind of crazy. Okay, but we don't care about this part. We just want this. So now we take 64 and multiply it by 3. It gives us 192. Right? Because that's what happened here. We took this, we divide 211 divided by 8 is 26 in some change, but we don't care about the 26 the change. Multiplied by 8 is 208. So did it just so happen? Yes, that's correct. So we take this and we divide it by the interesting octet, which is 201. Right? Yeah, 201. The interesting octet, which is 201, which is 3. Because the closest that's 64. Well, hold on. Let's double check that 64. 256 subtract 192 is 64. And then 64 multiplied by 3 gets us to 192 plus another 64 breaks it. So, yeah. So that means that our interesting thing over here is 192. Now, that doesn't mean that these things have to always match. Okay. So that means it's going to be 10. $218, $227, $201. No, not 201. $192. Now the amount of bits that we have free is 1, 2, 3, 4, 5, 6. So we have 6 bits free. So that's going to be 2 to the power of 6. That looks like 26 to the power of 6. $64. Again, I think that's just a coincidence. Usable is 62. Let's test it. Let's find out. See if I'm right. All right. 10.118.27.192. Hey! The first one that we've gotten correct. Oh, yeah. It feels good. So that means that all these other ones should be really easy. 10.218.27.193. Our last host should be 10.218.27. We just need to add 62 to this number, to 192. 192 plus 62. Yes, which equals 254. So that means that this is going to be 10.218.27.255 because that's broadcast, which means that this is going to be 218, 27, 1, no, 0, 8. Yes. 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 Let's fucking go. Let's fucking go. Okay. Hell yes. Hell yes. Okay. We're going to do one more. This is going to be the last one before we get to the flashcards. And yeah, now that we're starting to kind of cook with gas a little bit. Okay? So next one's going to be 27. Let's raise this up just a little bit. I need to get rid of that. And then make another one. It goes small again. Cool. All right, here we go. 154, 23, 87, 244, 27. Okay. So, like always, 8, 16, 24, okay, 25, 26, 27, 25, 26, 27, because 8, dang it, dude, I'm trying to make it not small at the end. Now that we have it written down, we can move this up. I hate. Oh, stupid. Okay, 8, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, and we can test that over here. So we have 8 and 8 and 8 and 3, which equals 27. This is where our line is. So that means that our network bits that are frozen is 20, not 26, 27. And that frozen bits is our side R. So that's 255, 255, 255. And then we got to add these together right there. Okay. So that's going to be 128 plus 64 plus 32, which is going to be 224, which is also going to be our masked value. 224. Okay. Our wild card is going to be these things. Going to be these. Okay. That is our bits that are free. This is going to be our wild card that's over here. So that's going to be 1 plus 2 plus 4 plus 8 plus 16 equals 31. Now we can test this. 31 plus 224 to equal 55. It checks out. Okay, these are all zeros because those are not being used. Okay, our interesting octets. Okay, our interesting octet is 4. It's right there. So that means our block size is going to be 224 subtract 256. Ooh. I think I just did that backwards. Yeah, I did. No big deal. Okay, so that's 2. That's 3. That's 0. We'll double check ourselves because I don't want to end the streak. 256 subtract 224 is 32. So now what we want to do is make sure or see how many 32s can go inside of this guy right here. So we're going to do 24 or 244 divided by 32. Okay, it's 7 and some change, but all we care about is the whole number. We don't care about the remainders. Okay, then we are going to multiply these two things because we need the number that's closest to it. Okay, so that's going to be 32 multiplied by 7, which is going to be 224. Again, that's a coincidence. I don't think that is always the case. No. No, see, like, that's not always, that's just a coincidence. I know it's happened twice now, but that is a coincidence. And why I'm saying it's a coincidence is because 32 times 7 is 224. But as we can clearly see, we have an example where 8 goes into 8 multiples of 8 only go up to 208 before it breaks 211. So it doesn't work, okay? So don't fall into that trap. Okay. So that means over here, go over here. Let's use the green again. Cool. The green, the bits that are free is 1, 2, 3, 4, 5. We have 5 bits free. Okay, so that is 2 to the power of 5. So 2 to the power of 5, which is 32. Our usable host is 30. So right here we have 1, 54, 23, 87, 224. That should be it. Now, the first host should be 225. And then all we do is add 225. And we add the usable hosts. 30. Well, we already used one host. So, really, it's 30. It's 29. Because the last host is going to be 254. Because we already used that number, right? Okay. Which means the broadcast is going to be 255. Okay. So we really should have added the 30 to the 224. Yeah. Okay, which means our next subnet is going to be 860. Let's stick it in. Okay. 154 plus 23 plus 87 plus 224. Are we correct? Woo! Okay. So that means 154 plus 32. Dang it, dude. 32, 87, 225. Okay. And what are we correct? Yes, sir. 154, 32, 87, and then it's going to be, oh, not 256, 254. I don't know why I wrote 256 down here. That's not correct. Yeah. It doesn't go to 256. 154, 32, 87, 255. Yes. 154 plus 32 plus 80, not plus, 86, 0. Dang it. Why did I hit 86? It should have been 88. Damn it. Damn it. Damn it. Damn it. Damn it. What? Fuck, I'm dyslexic. God damn it. I wrote 32 instead of 23. Oh my God, that upsets me so much. Okay, well, this is the part that matters. Okay, we did it. Okay. No, we don't want to save that. Excellent. We're done with this. Woo. Actually, I don't need that up right now. What we're going to do is some Anki flashcards. Bloop. I hope you're ready. I hope you are as enthused and as excited as I am. We need to have an Anki flashcard day. All right, we're going to do, honestly, the IPv4 header ones, I'm not going to lie, like, I'm probably going to do total trash on it. That was a lot of information. So, we're going to start here. Because there's only 17 of them. Okay, interfaces in Cisco device type are administrative down by default. That is the gigabit. Or no, it's the routers. Okay. I thought it was... Okay. Device type, not... Okay, anyway. Yeah, we're good. Okay, what is the formula to calculate the maximum number of hosts in a network? There's a formula for that? Oh, yes. 2 to the power of number of hosts. We just did that. Okay. Which IPv4 address class contains a total of 128 networks? Which class? D? Oh. What? 128 networks. Class A has a bunch of networks. Which IPv4 class contains a total of 128? I don't need this anymore either. Okay. Okay, we'll let that cook. Which IPv4 address contains a total of 16,000? See, this is what I'm talking about. Like, Class B. Interesting. Come on, Claude, talk to me. You're not wrong. You've just got two axes flipped. Class A networks are enormous in host per network, but there are very few of them. The flashcard is asking about the count of networks that count as tiny precisions because of each one is so big. The 32-bit pi is fixed. Every bit you spend on host is a bit you can't spend on networks. Here's the 128 column form. Class A uses only the first octet for the network ID, and the rule that defines Class A is that the first bit is locked to 0. That leaves 7 free bits in the octet and 7. Oh. That's what it means? And 2 to the 7 is 128. So that means that Class B is 16. So 2 to the power of 16. Is not that. But is it not to the power of 16? Is it to the power of 15? No. So then how is Class B 16,000? Class A network bits. So then it's got to be 2 to the power of something. So then why is it to the power of... Why is Class B to the power of 14? Oh, man. Same trick as Class A. One step further, Class B has 16 bits in it on paper, but the first 2 bits are locked to the pattern 10. That pattern is literally what makes an address Class B locked. Bits can't vary, so they can't distinguish one network from another. That leaves 16 minus 2. Oh, I remember this now. Now, I don't remember why it locks them like that, but it does. Okay. This is so much information. Oh my god. Which IPv4 address class contains a total of 2,000? I'm going to say Class D, but we're going to figure it out. So that would be 255 subtract 4. No. No, I'm going to say Class C. Yeah. Oh shit, it was right here. Okay, because it should be 24, but we subtract 3. So much information. Which IPv4 address allows a total of... It's got to be Class D. Hosts. Damn it. Read the whole question, Tyler. Which IPv4 address class allows a total of 60,000 hosts? I actually think that's C. No, it's B. I guess I could have done the math. That's got to be C. If an interface has the shutdown command applied to it, that what will the status column of show IP display? Down. Administratively down. The status field of the show IP interface brief command shows the layer blank status of the interface. Yeah, I gotta do that. Okay. I don't know. 1? Yeah, that was hard. Okay. We're going to finish these, and then there's some administrative works I have to do after this before I go to work. So this will be the only Ankis that we do. We will probably have a stream where all we do is the Anki flashcards. I know that's going to be super riveting. Everyone's going to love it. There's going to be tons of views. But it's what needs to get done. Okay? And we'll go through like all of them. Probably multiple times. It's gonna suck, I'm not gonna lie. Okay, the protocol field of the show IP interface brief command shows the layer blank status of the interface. Yeah, I need to go back. The blank field of the show IP brief command shows the layer 1 status of the interface. The status field. I need to do some more packet tracers too. There's a lot of things I gotta. Protocol. The protocol field. Yeah, I'm not gonna lie, dude. I don't feel good about these. Interfaces on Cisco device types are not administratively down by default. Ports. Switches. Device type. Damn it. Ports on switches. Command to configure an IP address on an interface. R1 config T. Isn't it just IP and then you type it? No, it's config IP address and you type the address. IP address and then you type it. Yes. Command to configure a description on an interface. Isn't it description and then you just put it? No, there's something that you put before it. No, it's not. You just put description. And people put hashtags in order to make it easier to see. Interfaces on Cisco devices are administratively down by default. Routers. More. Oh, wow. There's a lot of options I have here. Anyway. Display the configuration description of each interface on the router. Show interface descriptions. Each IPv4 address class contains a total of 128 networks. A. I think we looped back around. We did. Okay, we looped back around. We're going to leave it right there. Yeah, we're going to leave it there for today. There's some administrative things I got to take care of before I go to work. So hopefully I can take care of that stuff. If you enjoyed the streams, If you're enjoying the stream, awesome. Thank you very much for coming and hanging out. I really feel like we mastered the subnetting. Okay, we'll do a little bit of subnetting every single day, maybe at least one, maybe two, especially now that we've kind of got it zeroed in. Now it's time to do, like, honestly, the subnetting part's kind of the fun part. It is the other stuff is not fun. The memorizing the protocols and all that stuff. That is the next step. That's what we got to do. I do have some videos that I'm trying to get pushed out for the channel. I know that it helps out a lot of people. There's a lot of positive comments on them. Thank you so much for all the love and good feedback with all of them. If you're working on your Network Plus for CompTIA, go check out some of my labs. I don't have them all up yet, but I do have quite a few. I have some other videos that are going on that kind of explain things. I try my hardest to make it as short, simple, and sweet as possible. So go check out my channel, Tyler Lemmond. Subscribe, like, all that good stuff. We will be playing Halo again tomorrow night at 8 p.m. if that is something that interests you. If not, the next study stream will be Monday, and we're probably going to be doing more study streams, more than just 2 times a week. I just haven't figured out the times yet or the days. So just be on the lookout for that stuff. Yeah, I usually have it posted on the channel when the next stream is coming up. The week before, I try to post all the streams that are coming up that week, so that way you have an idea of what's going on. Other than that, that's what's happening. I hope you guys had a lot of fun. Please like, subscribe, share, all that good stuff, and I will catch you guys later. And oh, remember, work with what you got, build what you need. It wouldn't be split because it's not over 15, so it wouldn't be split. Now it might try to make it go split, but you can put the command that makes it not split. That also sounds oddly familiar. I think that exact example was in the video with Jeremy's video. I would and I think he forced it to be split. So I hope that answers your question. I saw that right before I left. I wanted to answer it. So hopefully that answered your question.